Bismillahirrahmanirrahim. Today we are going to study the synchronous generator, introduction and its construction. As we already studied the induction motor, and in motor we study the main parts of the motor are the rotor and the stator. Similarly, in the construction of the synchronous generator, the main part, one is the rotor and other is the stator. Rotor and stator. Principle of the synchronous generator. In a synchronous generator, a DC current is applied to the rotor winding, which produces a rotor magnetic field. There is a rotor rotates by the turbine, and turbine was rotated by some external source, either water, either thermal energy, either steam, or whatever. The turbine is rotated by some external source, and this turbine shaft is connected to the rotor, and then rotor rotates. The magnetic field on the rotor is generated by external DC supply. Thus, now magnetic field is rotating. This magnetic field cuts the stator winding and induces a voltage in the stator winding. Thus, voltage is induced, and the mechanical power is converted into electrical power. Now, to make your concepts more better related to the generators and turbines, I want to show you some pictures. I think I showed these pictures and videos to you before, but here I will show you again. This is the shaft. On the lower side it is connected to the turbine, and from this side it is connected to the rotor, and this is the turbine. This picture is taken at the time when the turbine is lowering to its position. This water strikes at these blades. These are the runner blades, and it starts rotating, and when it starts rotating, the whole shaft starts rotating, and rotor is present at this place, and rotor starts rotating, and stator will be present in this outer side, and then this rotor, the magnetic field on this rotor induces voltage in this stator winding, and it will be collected by at the end towards the transformer and then supplied to the 132 kV transmission lines. So now here I am showing you the shaft and the turbine. Now these pictures are very important pictures. This picture is taken from inside the tunnel. This is the spiral case. The water comes from approximately 60 meter height, and at the end water reaches at this point. At this point the tunnel have an opening with gates like that, and water moves towards this point gradually. This is the inner picture of the tunnel, and this is the outer picture of same thing. When water comes at this point, and water moves there and moves down, and here turbine is present, and when water strikes this turbine, the whole turbine starts rotating, and shaft is present on the upper side, and whole shaft starts rotating. These are the very important pictures, and I think this can be made only when the power plant is in construction phase. Now we can't access at this point. Now this picture, that after some construction, these gates look like in this way. These are the same gates of the tunnels. We called it as wicket gates. Through these wicket gates, water control which strikes the turbine. And this is the upper part of the shaft. At here the rotor will be present, and yes, so this is a video. This video is taken when we are lowering the turbine towards its position. Yes, so these are some practical pictures related to this generator shaft and turbines. I think you will better understand now that how generator rotates and how rotor rotates. So the moving towards the windings of the synchronous generator, two terms commonly used to describe the windings of the generator. One is the field winding and other is the armature winding. What is the field winding? Field winding. Field winding applies to the windings that produce the main magnetic field in a machine. As in a synchronous generator, the main magnetic field produced on a rotor, so the rotor winding can be called as field winding. The other winding is the armature winding. Armature winding applies to the windings where the main voltage is induced. As the main voltage is induced in the stator of the armature winding, as the main voltage is induced in the stator of the synchronous generator, so stator winding can also be called as armature winding. So after discussing the windings, the next step is to discuss the types of the rotor. The rotor of a synchronous generator is especially a large electromagnet. This is the important word, electromagnet, not permanent magnet. When we supply the DC current, then it will become magnet, otherwise it is not a magnet. These magnetic poles on the rotor can be of either salient or non-salient. Salient, the term salient means sticking out, and a salient pole is a magnetic pole that sticks out from the surface of the rotor, like this. These rotors are sticking out from the surface of the rotor. These poles are sticking out from the surface of the rotor, so these are called salient pole rotors. These rotors are normally used in the generators where we need high number of poles. On the other hand, the non-salient pole is a magnetic pole constructed accordingly with the surface of the rotor. As shown in the figure, there are no salient poles sticking out from the surface, and these poles and these rotors are used for 2 or 4 poles, and these rotors are normally used in the thermal turbines, because in thermal turbines the speed is very high, and speed is very high, so we can produce the same amount of frequency by the high speed and low number of poles. But the salient pole rotors are normally used in the hydro power plants and hydrosynchronous generators, because the RPM is very small, and these RPM is very small, speed is very small, so high amount of poles are required to match the frequency. As we know the formula of frequency, N is equal to 120 F/P. So making this frequency, these poles are adjusted according to this speed. Now I will show you the practically how the poles and rotor look like. This is the pole, you can see in this figure. In this rotor there are 26 pole rotor, and one pole look like in this way, samely like this. In this picture we are testing the winding of this pole one by one, and all poles are tested and its winding are tested, and then we pass the pole for the installation. This is the core of the rotor. Core of the rotor has same laminated steel. At this point the pole will be attached, and then poles will be attached on these slots, and this is the core of the rotor. The core of the rotor look like this in the construction phase. Here the rotor will be attached to this shaft end. This is the pole, one pole. One pole is moving towards the rotor to attach. Here I was in charge of checking these poles and its winding, and I am checking the reading and clearing the tests of this rotor pole. I am giving tough time to these Germans, you can see about their faces. So this pole have a winding problem. It did not clear the test, so we rejected that pole. So that's how the rotor poles looks like. I show you the practically picture of these poles. Now this process is they are using to heat the pole winding. So in this way its resistance will improve, winding insulation resistance will improve, and poles will clear the winding test. A DC current must be supplied to the field circuit on the rotor. Since the rotor is rotating, a special arrangement is required to get the DC power to its field winding. So for this arrangement there are two common approaches. One approach, I think you already know about this, we study in the induction motor also. Supply the DC power from an external DC source to the rotor by means of slip rings and brushes. Another approach is that the same DC power from a special DC power source mounted directly on the shaft of the synchronous generator. The first slip rings and brushes look like this. Like these are the slip rings and this is the brushes. Slip ring is rotatory but brushes are stationary, so in this way power is transmitted from external circuit through slip rings to the rotating circuit. Practically it looks like this. These are the slip rings and these are brushes connected from the stator side, and the current is transferred from the external circuit to the rotor winding. Anyhow, I can show you this practically to near power plant. So here it is telling that slip rings are metal rings completely encircling the shaft of a machine but insulated from it. The same one end of the DC rotor winding is tied to each of the two slip rings and a stationary brush rides on each slip rings. Brush. A brush is a block of graphite carbon compound that conducts electricity freely but has a very low friction so that it does not wear down the slip ring. So this is the brush and the slip rings. But this arrangement have few problems. One problem is that the maintenance is required because after some time there is a friction takes place between this brush and this sliding rotating slip ring. There is the friction takes place and wear and tear takes place at this point, and this amount of this brush will become smaller and brushes will consume at this point. So proper maintenance is required to change these brushes. In our power plant, in every month we did this kind of maintenance and change these brushes if required. Anyhow, in practical experience I saw that the positive terminal, the brushes at the positive terminals consumes more than the brushes on the negative terminals. So we just change somehow negative, put on the positive side and attach positive which you already consume on the negative side. So in this way the life of these brushes increases. On larger generators and motors, brushless exciters are used to supply the DC field current to the machine. How it works? A brushless exciter is a small, it is also an AC generator with its field circuit mounted on the stator. Like this. This is the stator and field circuit is mounted on the stator, and the external DC supply is connected to this stator winding, this stator circuit of this field winding, and its armature circuit mounted on the rotor shaft. Like this. Armature circuit is mounted on the rotor shaft, and this rotor shaft is rotating, so this field winding induces voltage in this AC voltage in this exciter armature, and this AC voltage is rectified, and after rectified it is connected to the main field winding of the rotor circuit, and this main field winding then induces main voltage on the stator winding. So that's how, by adding an mounted AC generator with its field winding on the stator and its armature winding on the rotor, a brushless exciter system is introduced and used on the larger motors and generators. Many synchronous generators that includes brushless exciters also have slip rings and brushes, so that an auxiliary source of DC field current is available in emergency. In case of emergency that internal mounted AC generator is not working, so the external DC supply can also be connected through these slip rings and brushes in the emergency case. So synchronous generator stators are normally made of preformed stator coils in a double layer winding. Preformed stator coils, double layer winding. I will show you practically, otherwise it is difficult to understand. The winding itself is distributed and ordered in order to reduce the harmonic content of the output voltage and currents. So the stator winding looks like in this way. This is the stator core, and some slots are present, and in one slot two preformed stator coil, which we call the stator bars, winding bars, are present. One bar is connected to other bar, and other bar is connected at other place on the inner side. So these two bars are not connected to each other, these are insulating to each other. One is connected to other bar, who is connected move to other slots in the inner phase. So that's how the windings are of the stators designed and look like. This is also the stator bars. Same, these pictures were taken in the time of construction. Now it is difficult to reach at this point because here rotor is present and air gap is very small, so rotor approximately reaches towards this stator winding. Yes, on a bigger picture, that's how the stator look like. This is the core. Inside the core, these are the slots. In one slot, two bars are present. One bar which is present here on the upper side, here connected to that bar which is goes there towards the inner side. So this is means double layer winding. So that's how the stator of the synchronous generator look like and its winding looks like. Now the next topic is the speed of rotation of synchronous generator. As we already studied in the induction motor about this formula, that the synchronous speed is given as n is equal to 120 f over p. In this synchronous generator there is no slip, as the rotor magnetic field moves approximately with the same speed as the rotor moves, so it induces the frequency in the stator approximately the same. So there is the fixed frequency induced Fe frequency, so here can be calculated as Nm P divided by 120. But here one thing is very important, that generator must turn at a fixed speed depending on the number of the poles on a machine. As I saw you in the picture of the pole, number of the poles already made on the rotor during the construction phase. So this is the fixed, this is the fixed, and now frequency is directly proportional towards the speed. So this speed can control the frequency. So it is the very important parameter, because if speed change, frequency change, and if frequency is 50 Hz, even frequency reach towards 49 Hz or 48.5 Hz, the protection system will operate and the unit will be shut down. So NM have to be operated at this speed, and this speed is controlled by the wicket gates which I showed you in the figure, and these wicket gates controlling by the highly sensitive governor. So governor already knew that how much the amount of the gate is open, that the amount of water is released which strikes the turbine, so that it produces the frequency of 50 Hz at the given load. And one important parameter is that the load, as load varies, so now the more amount of water is required to produce the same speed and same frequency. So this is the working of the governor in the power plants. Now we are going to study the internal generated voltage of a synchronous generator. The voltage generated on the stator winding is given as EA is equal to K into phi omega. The internal generated voltage EA is directly proportional to the flux and to the speed, but the flux itself depends on the current flowing in the rotor feed circuit. So its graph can be given as if this is IF and this is the flux, so IF increases, flux increases. Same goes towards, as this flux is directly proportional to EA, so if this is the generated, this is the field current. So when IF increases, the generated voltage, induced voltage increases. So this is also one very important parameter, that by controlling the IF we can control the generated voltage, and by controlling the NM we can control the frequency, and by controlling IF we can control voltage. So these are two controlling parameters of the synchronous generators. So now that's it from this lecture. Thank you.